Okay, so let's continue now to calculate the efficiency of protocols. So we have now an understanding for what the efficiency is for stop and wait. So this is so this is the end result. The efficiency looks like this in the error-free case, and the difference from the error-free to the case where we have independent frame errors is essentially that we pre-multiply with 1 minus PF, PF being the probability of losing a frame, and then we ignore the probability that an ACK could be an error also. So let's go now to the main problem with this protocol here, stop and wait, is that the time from here to here, the transmitter is idle. It does nothing. It just waits for the acknowledgements. And then if we have full duplex communication, as we assume already in the course here all the time, this time could be spent on transmitting frames instead of waiting for acknowledgements. So this is exactly what go back N does. Go back N starts to transmit the next frame here, and when that's completed, the next frame, and so forth. It keeps on pumping frames out on the forward link, the link from the transmitter to the receiver all the time, and then just hope for the best that these will eventually be acknowledged. However, if there is a frame error, then the go back N transmitter needs to go back, that's why it's called go back N, a number of frames and retransmit them, right? Because the receiver has no buffering capability, okay? And the receiver will not accept any frames which are out of order, even though they are error-free. So to figure out the efficiency in stop and wait, it's instructive to first have an idea of what's going on when there are frame errors. So let's draw a small time axis here, where this is the first frame that we transmit. It has some duration, TF, right? And then we keep on transmitting these. Okay, and then what's going to happen is that on reception here, there will be like the diagram that we have here. So at some time later, or let's do it like this. We then keep on transmitting these frames, keep on transmitting like this. Now, suppose that the turnaround time is like this, T0. This means that the first frame will be acknowledged here at this point in time. So the send window needs to be big enough to, in this case, have at least 3 packets in it, right? Because we need to keep on transmitting until we get an acknowledgement for the first packet, and then we can slide the window, okay? And then we can just store this one, and this one, and we keep on going like this. So the time from here to here is the we select this as the timeout, which is how long is this timeout? Well, in this case, it's 3 packet durations. So in general, we take the turnaround time, the round trip time, and divide it by TF. And if that's not an integer, then we round this up. Okay, so in this case, it happens to be 3, right? So T0 divided by TF is 2 point something, and then we round it up to 3. Okay, so the timeout here is then this number, whatever it is, times TF. Okay, now suppose then we're unlucky, and this packet is lost, okay? What will happen then is that at timeout here, we have not received an acknowledgement for packet number 1, and then the transmitter needs to go back and retransmit all outstanding packets at this point in time. And all outstanding packets in this point in time is 1, 2, and 3. Okay, so you will retransmit 1, then 2, and then 3, like this. Okay, so these are retransmissions. And then suppose that this packet is also lost. what will happen then? Well, the process would repeat itself. So packet number 1, packet number 2, etc., like this. But if this packet is now received correctly, okay, it will be acknowledged a little bit later here. But if this one is received correctly, then this one will never ever be retransmitted, right? Because then packet number 2 might be retransmitted. We don't know that yet. But if this one is correct, I mean, this one is lost, but this one is not, then the time when this packet is delivered is exactly here. Because now we can keep on working with packet number 2. And maybe that's delivered, maybe this is in error, maybe this would trigger retransmissions and so forth. But the time it takes to deliver a packet is a number of these timeouts plus 1 frame duration until we can move on to the next packet. Okay. So how many timeouts do we need? Well, what we can do then is we can do as we did previously. We can calculate how many times we need to transmit frame number 1 until it's done. And that is 1, 2, and 3 times. Okay? 2 consecutive errors and then 1 success. And then there is a bunch of things that goes on in the middle also. But let's just count frame number 1 here. So it's 1, 2, and 3. So the total time to deliver something in go back n is nt, the number of times it takes to transmit frame number 1 until we're done, minus 1 times the timeout. That's this one and this one in this case, plus a final frame duration for completion. I missed one crucial point here. Yeah, okay. And then let's write this then as nt minus 1. And then the timeout, we can write this as some number n times tf, where n is this number. We round up t0 divided by tf. So we have here n times tf plus tf, like this. And of course this is equal to tf times 1 plus nt minus 1 times capital N, like this. Questions so far? Okay. So this is actually the tricky part, to figure out the time it takes to deliver a packet in go back n. And there are a few things that I sort of pushed under the rug here, because what I said here is that this assumes that no errors have occurred before I started to transmit packet number 1 here. Because there could be errors in other packets that could trigger other transmissions and so forth, right? We have ignored these. So this is a little bit of a approximate analysis, but it's good enough for our purposes. We just want to get a feeling for what the efficiency is. Okay, so now we're actually done here, because what do we have here? This is the time, and here's the random variable, nt, which has the same statistics as it had in stop and wait. Okay, nt tells us how many frame errors that have occurred for frame number 1. In this case, nt is equal to 3, right? 2 errors and 1 successful. Okay, so then the expected value of go back n delivery time is then the expected value of tf 1 plus nt minus 1 times n, like this. We write this as tf times 1 plus the expected value of nt minus 1 times n, and parentheses, We know what the expected value of nt minus 1 is. It's on the top of that, right? It's pf divided by 1 minus pf. So this is pf divided by 1 minus pf. And then it's just algebra from here. And the end result is that we have tf times 1 plus pf n minus 1 divided by 1 minus pf. All right, so now we know the expected time it takes to deliver a packet in go back n, and it's this expression here, which depends on tf, on pf, and on n. And n is the size of the send window, or actually it's the, it has to do with the timeout, but in this case it's also tied to the send window. Okay, so what we're after is then the effective rate for go back n, which is then nf minus no divided by the average time it takes to deliver the packet. So the expected value of t go back n. And then it's 1 minus pf, 1 minus no divided by nf, tf times 1 plus pf times n minus 1. So what I did here is, basically took this result and wrote it like this, and then I divided. No, this cannot be true. Sorry. It should be nf minus no like this. Okay, here we go. Okay, and then let's recall what TF is. What TF is R divided by NF. R is the data rate and NF is the number of bits in the frame. And then we can divide through, break out R and, sorry, let's do that again. TF, the frame time, is equal to the number of bits divided by R. Right? That's the frame time. So let's put that into that and simplify a few things. And then we get 1 minus p, we take the rate R, and then it's 1 minus pf, and then 1 minus no divided by nf, and then it's 1 plus pf n minus 1. I just simplified a few things here. Right. Okay. So now we're ready to compare this with the stop and wait result. So we have that the effective, okay, so one more thing perhaps. What is multiplying R here is the efficiency of go back n. So the effective rate is the rate that we had from the beginning multiplied with the efficiency, and the efficiency looks something like this. So it's this 1 minus pf again. Okay, so if we had error-free transmission, we should be very good, right? So let's check that. If we put in pf equal to 0, we can forget about this term, and we can forget about that term in the denominator, and we have r times 1 minus no divided by nf. And this is the best we can ever hope for. Right? It means that every frame that we transmit basically it's yes, it's the best we can hope for, because we always have this overhead NO that we need to account for. So if you didn't follow me here, just think about this. If we put PF equal to 0, this would be the best we can ever hope for any protocol. Okay. The problem is that when PF starts to increase, we still have this factor in front of it, just as we had in stop and wait, but we also have this factor here, which is multiplied by n minus 1. So n minus 1 could be a fairly large number. It's the number of packets we have in the send window. So my conclusion from this, our conclusion from this, is that the efficiency for go back n and the data rate for go back n, the effective rate, is very nice if PF is relatively small. When PF increases, this penalty here that we have in the denominator will eventually do this protocol a big disfavor, right? So after a while, this is no better than what we would get then in stop and wait. Okay? So go back n is better than stop and wait, but if there are many errors, it's not so good anymore. Okay. So how about selective repeat then? Okay, and the reason why it's not very good when we have errors is actually here on the here already, right? So if we have a frame error here, then we have to retransmit all packets, even though 2 and 3 perhaps receive the receiver without any errors, we still retransmit them here. Okay, so how can we avoid this? Well, then we do selective repeat, which means that if 2 in the original transmission was received correctly, it's put into the receive window and buffered there until packet number 1 has been received correctly. So selective repeat should be much better than go back n in that case. And as a matter of fact, one can reuse this whole analysis and just put n equals 1, and then we get the performance for selective repeat. Okay. So for selective repeat, the delivery time is as for go back n, GBN, but with n equals 1. Because each error we do triggers a retransmission of exactly one packet, namely that packet that was in error, not any else, right? Otherwise, it's the same analysis. So then the effective rate for selective repeat is written here. It's just that we put in n equals 1. And when we put n equals 1, we get rid of this troublesome factor and the denominator. And then we get r times 1 minus pf times 1 minus no divided by nf, like this. Okay, so selective repeat is, of course, penalized when pf increases, but not to the very same degree as go back n, which is heavily penalized when we have errors. Questions? So the whole analysis we did now is about figuring out the average time it takes to deliver a packet. We did that for stop and wait, we did that for go back N, and then we did that for selective repeat. Selective repeat turns out to be a special case of go back N, right? And the idea is that once we have figured this one out, we can calculate the effective rate. And then we get a number of expressions here. And we see that the efficiency for selective repeat and stop and wait are these type of expressions. That's what pre-multiplies are here, just as we had here. And we see that when we have errors, we typically get this factor 1 over 1 minus PF in front of an expression, efficiency expression. So efficiency decreases when we have frame errors, which it should be, right? Then the question is there anything more that affects this? Well, in stop and wait, it turns out that there is nothing else here in this expression that depends on frame errors. So it's relatively insensitive to frame errors. Okay, stop and wait. While go back N is quite sensitive to frame errors. However, if we don't have many frame errors, then go back N is better than stop and wait if there is significant idle time. Okay. If there is significant idle time and lots of frame errors, then by all means let's go selective repeat, right? Because that would be the best. Now, why shouldn't we do selective repeat always? Any suggestions? There we go, costly, right? Why ever use something which is less than the best? Because the best is too costly, right? So here we need buffers, more complicated logic, and so forth, right? Stop and wait, the simplest you can think of. So if the idle time is not too bothersome, by all means go stop and wait. If the idle time is significant, try go back N. If on top of a long idle time, you have lots of frame errors, you have to go selective repeat if you want to be efficient. Okay. So of course, and this means also that the choice is not clear, it depends on the situation, and therefore all of these are used in practical protocols, depending on the situation. Okay. So that more or less does it for retransmission protocols. Okay, and we have a few other things to clean up, some details which are practical details which are important, but the big things are done now. And the first thing I would like to talk about is when we have bidirectional links. Now we already talked about, we had one transmitter and one receiver, and we talked about this protocol. So if we have one transmitter A and a receiver B, we have some oops, this is not what I wanted to do. We have some protocol that sends service data units and sequence numbers and get acknowledgements back. So this is some ARQ protocol running here. And it's these sequence numbers and ACNO, depending if it's selective repeat or go back N or whatever, had different meanings, but this is essentially what's going on. Now, if we have at the same time data going from B to A, then we have another protocol which is running below here, which is sending data in the other direction and receiving acknowledgements in the other direction. This is fairly common that we have this, right? We communicate back and forth, right? And we want reliable transmission in both directions. The problem, okay. So the thing is that sending an acknowledgement, although it's not many bits, it's still an overhead that could be significant due to all the headers that is needed to transmit this acknowledgement. So if this acknowledgement could hitch a ride on anything else with another packet which is going in that same direction, that would save on overhead. And that's exactly what piggybacking is. So the piggybacking is that we squeeze in this acknowledgement inside an information frame that's going in the other direction. Just as we take this acknowledgement, which goes from A to B, and we stick that in to hitch a ride with the information frames, which is going in that direction anyways. And this, by doing this, we save on headers and overhead and so forth. So this is quite used actually in practice. So at the end of the day, it looks something like this, that an information frame that goes from A to B carries payload and sequence number, just as it always does. But it also could carry an acknowledgement field here. Okay? And that acknowledgement belongs to the blue protocol, and the blue protocol is sending data from B to A, right? And in the data that goes from B to A, it's the the information frame that goes from B to A contains the payload, the sequence number to that payload, but also the acknowledgement number, which belongs to the green protocol, which is going in the other direction. So this is called piggybacking, right? You know piggybacking when you take a person on the back and you run with that person. That's piggybacking. All right. I don't know what the pig comes from, but anyways. Now, something else that we haven't talked about is that how do we know that we are synchronized at the start of things? How do we synchronize the pointers that we need, the state variables and so forth? So there is actually an establishment procedure before we can even start the ARQ protocol. So stop and wait, go back in and select the repeat are connection-oriented protocols. Okay, so what was this again? Connection-oriented protocols. It means that there is a setup procedure before data can actually be transmitted, and after the data, all data has been transmitted, there is a teardown procedure. Right? You set up the connection, you use the connection, and then you tear it down. Right? And this is in logical sense, right? There is no necessary cable